So in this video, we are going to talk about how to graph a piecewise function and explain what a piecewise function is. A piecewise function is simply a function that is defined in parts or pieces of more than one function on different domains. Meaning you might have part of the graph that's quadratic, but part of the graph that's linear, and then another part that is an absolute value function. And those domains are limited based on what you see. It is written as a list of different functions with the different domains included. So what does it look like? What does the function look like? Here's an example of a piecewise function. And you can see here that we have a cubic function. We have a linear function. And then we also have a square root function. So the question is how do we go about writing what this equation looks like? Well, my best advice to you is to pick points on the function that are clearly defined, okay? The open circles will be drawn for you, so you know where those are. And make sure that you have a function that has an a value of just 1. So you can see here that it has an a value of 1. This one also, is 1. But it's going the wrong way because it's going down as opposed to going up. So we'll have to accommodate that. So the first thing I'd like to do is identify, well, what is this? This is x to the third power. This right here is a horizontal line. And students do have trouble sometimes with the difference between horizontal lines and vertical lines. So what I like to help people out with is the mnemonic device called Hoy-Bucks, which says horizontal lines have the equation that is y and slope of 0, where vertical lines have an undefined slope and equation that is x. When you do piecewise functions, you have to have an equation that's written as y because the function notation f of x is y. So just keep that in mind. Okay, so this is the equation y equals, in this case, 2. And the last function here, this is a square root function. So to build what the function is, we're now going to find the vertex points for each of these. So my vertex for this function is at this point. It really helps to label. And so that would be -3, 0. So now I can go ahead and label what this function is. This function is f of x is equal to, remember h is -3, so when I put the negative into the parentheses, it would be negative, so +3. It is a cubed function, and it does not have a k. But keep in mind that a cubed function should be 1, 1, -1, -1. So this one is actually going the wrong direction, or it's reflected across the x-axis, so we need to put a negative on it. The middle function here is just y equals 2. So if you want to write that as a function, it would be f of x is equal to 2. And then the red function is a square root, so we would write that as f of x is equal to where its vertex is accommodated into the square root function. So the vertex here is 2, 3. So this is h and this is k. And so I would have x minus 2 plus 3. And so the next part, the only part that's new, you've probably already described functions using vertexes before. So the next part that's new is describing the domains, which you've also already done in a previous unit. So if I look at this domain, the domain of this function is -infinity and then stops at -2. So the domain of this function using integral notation is -infinity to 2. -2, that is. And the domain of this function is just from -2 to 2. Using integral notations, we would have brackets on that one because of the fact that it is a solid dot. And then this one goes from 2 to infinity. So the domain of this one would be 2 to infinity. So now all we have to do is just write all this information in one organized way. And the way you do that is you have one f of x, because they're all actually f of x. And then you state the function. You can see this function is here. And then once you do that, you state the domain. Now, what's interesting about the domains in these problems is We typically in Algebra 2 or higher level classes, we use interval notation. But within a piecewise function, you can't put parentheses here. So you have to switch the interval notation to this. It's kind of like set notation, but it's more of this inequality notation maybe. So this thing is the same thing as saying negative infinity to negative 2 is the same thing as x is less than negative 2. And then here we put our function 2, we put it in here, and our domain was negative 2 to 2. So remember, when you have something between in math, between is two less than signs, right? This is between, so we would have two less than signs to mention that. You might remember that from the absolute value conversation about equations and solving. But we have equal signs because of the bracket. In this last one, we have the square root of x minus 2 plus 3, which we already had here. The domain here would be 2 to infinity, which would be 2x greater than 2. So in this video, we're going to go ahead and take a look at some examples of how to graph a piecewise function given the equation already here, and then also look at how to evaluate functions, piecewise functions at particular values. So the first thing you have to understand is it would really help to sort of sketch, like, well, what is this? This is a line starting at 1 going downward. So it helps to sort of just get an idea of what the picture of these looks like before we put them on a graph paper. If I think about this graph, this is a graph starting at the origin going upwards with a slope of 1 over 2. So now that I know that, there are two ways to do this. The first way that some students will do is they will go onto the graph and actually graph exactly what they just did. So they'll go to 1, they'll go down 2 and over 1, and my advice would be to fill the entire graph paper up with those dots being produced from either the slope or later when you have a parent function. So that is that function. And then if I do the green one would start at the origin and go up 1 and over 2. Up 1 over 2. Just a little review of how slope-intercept works from Algebra 1. So now I have these two graphs that I sort of modeled here on the graph paper. And now what I want to do is I want to take my eraser and erase anything that's not in this domain. But before I do that, I want to think about what this domain is saying. This domain is saying that you want to use a solid dot and graph everything that is before negative 1 on the x-axis. Where this graph is saying use an open circle and graph everything that is after 2 on the x-axis. So when I think about that and I get my eraser out, I want to go to negative 1 on the x-axis. And I want to basically keep only these two dots and erase these dots because they are the dots that are out of this domain. And for this one, I want to go to 2 and only keep the ones that are greater and erase these dots that are not in the domain. Then I would want to come back and actually sketch the graph in here and just be careful when you go to here. So like this part, when I sketch that part, I'm going to need to be careful because it currently has a solid dot from when I recorded what that line looked like over the entire interval. So I'm going to want to go back and just make sure that I erase that dot and actually make it open circle. So the other way, when you get a little better, is to do it like this. So that's a great way to start, but as you get a little bit, and some students just like one way versus the other. The other way is to figure out where this point actually is. So the way you would do that is you would take negative 1 and you would plug it into here. So if we plug negative 1 into this function, we would have positive 2 plus 1, which would be 3. So what you would do is you would graph that point as a solid dot, and then you would use the slope in reverse because it's going to the left. So you'd go up 2 and then negative 1 that way. Remember, the slope can be down 2 and over 1 as for that, but it could also be up and then back because this is a negative, but this is also a negative, so that would work. And so to do this one, you would put 2, so you take 2 and you would put it into this function. So if I plug 2 into it, I would have 1/2 of 2, which would be 1. So I would take the point 2, 1, and I'd graph an open circle, and then I would use the slope up 1 over 2 to graph it. So you can go directly to this graph, or you can subtract it. All right, let's take a look at one that has a little bit more parent functions in it. So to do this, we're going to do the same thing. We're going to give a little sketch of, okay, well, what does this look like? This is an absolute value going downward. It's going to be a V somewhere on here. This graph right here is a horizontal line. Keep in mind that you really can't have vertical lines with piecewise functions because it says y equals 3, which is a horizontal line. And then for the last one, we have a quadratic, and it is going upward. So I'm going to go to, and this is where we have to be careful, you have to make sure you also know where the vertexes are. So this problem right here has a vertex of 0, 0. I don't really care about the vertex for the horizontal line, but this one has a vertex of 2, 0. Remember, H is always opposite. I see a negative. It actually is going to be graphed at positive. So then I'm going to go to 0, 0 on my graph, and I'm going to fill it up with the dots that this will be. And this might take some students longer than others. So some students might have to go 1, 1, 2, 2, and then negative 2, 2, and then multiply by negative 2, and they will end up doing this, right? So this one that's here will be here. This one that's at 2 will be at negative 4. So you might have that might take a little longer for some students. Some students might go directly to these dots, but then you need to make sure you go back and erase the practice ones. So we started at 0, 0. We were supposed to go to 1, 1, but it was multiplying the output by negative 2, so it went 1, negative 2. And instead of going 2, 2, we multiplied the output by negative 2, so 2, negative 4. We'll come back and deal with the domain in a minute. So for the horizontal line, we would just fill up the entire graph paper with 2's, right? So we have 2's all the way across here. Make them as horizontal as you can. All right, and then for the last one, for the quadratic, we are going to go and graph that one at its vertex of 2. This one's just a normal quadratic, so 1, 1, negative 1, 1, 2, 4, because square root of 2 is 4, then negative 2, 4. Now, if that's too many dots for you, just make sure you draw lightly and make sure you erase carefully. So now we're going to go back and we're going to understand what this domain is saying. Again, it really helps. It really helps to understand that when I do this, I want to keep a solid dot here. And notice that I'm labeling the problem before I'm actually doing anything on my graph. That's an open and then a closed circle, and then this one will be open. All right, so now I'm going to go use my eraser, and I'm going to go to my absolute value graph, and I want to keep things that are left of this dot. So at negative 1, I'm only going to keep this. I'm going to go back and erase these because they're to the right. For this graph right here, I want to keep things between. Remember, double less than signs and notation in mathematics means between. So I want to keep the one from negative 1 on the x-axis to 2. So anything that's not in between negative 1 and 2, I'm going to erase. And then for this one, I want to keep anything larger than 2, which is actually at the vertex. So I'm going to erase these pieces. And now all of a sudden I have a nice cleaned up graph other than one little thing. So if you want to, you could, make those open now. I like to kind of wait till the end and as a double check, so I always check it. So this was an absolute value, and it was headed down this way. This one right here is a horizontal line. And this one was a quadratic. Okay, so now I'm going to go back and erase the ones that need to be open. So that one should be open, and this one should be open, and I'm going to make sure that I do that. And of course, that's just your preference. If you want to make this open before you start, you can. My preference is to do it when I do it, just to double check to make sure I have it right. So it comes out looking like you did a whole lot of math there, but in fact, what you really did was just graph 3 graphs and erase pieces of it. The other way again would be to put this value in here. You have negative 1. You put negative 1 into the absolute value, it would be 1, and then you would get negative 2. And then you would graph the absolute value from there using that. This one, if you put stuff into a horizontal line, remember you're just going to get 3 as the output. So you put in negative 1, you'll output 3. You put in 2, you'll output 3. And you would just connect the dots, open, closed. You put 2 into here, you would get 0. 0 squared would be 0. So you put 2 in here, and you would square that and get 0. And so that point corresponds to here, and then you would graph the rest of the square using the key points. So that method that I just showed you there is very helpful when we talk about the evaluation portion. So what I did was I took these graphs and I just wrote them down here. What if I didn't have a graph? How would I evaluate it? And the way you would do that is you would take -1 and you would plug it into the domain first and see if it's valid. So if I take -1, is -1 less than or equal to -1? Or is -1 a greater number than 2? So it's true here, and it's false here. So you would not do this problem, and you would only do that portion. So you would have -2 times -1 plus 1, and then you would just evaluate that using Gelmdas. So you would have 2 plus 1, or 3. So to take a look at the next portion, again, you just kind of have to start that process over. So to take a look here at 13, where would 13 go? Well, you come up here and you say, well, is 13 less than -1? The answer is no, it is not. Is 13 a larger number than 2? Yep, sure is. So I will evaluate this problem with this portion of the function. So I would have 1/2. I inputted 13. So that would give me 13 halves, which you just can just leave it like that. I don't need to know that it's 7.5. In fact, if you say 7.5, it makes it a little more obvious that you're using a calculator, and basic skills like that, you don't need a calculator for. So what happens with 0? Well, when I do 0, I want you to show you what happens. It's actually not valid in either statement. So is 0 a smaller number than -1? Nope. Is 0 a greater number than 2? Nope. So this problem does not exist. It has no output value. It does not exist. Why is that? Well, if we go back and look at the graph, remember, I'm trying to evaluate this part of the graph. There's nothing in there. So you can see it very easy visually, but algebraically, sometimes it gets a little bit confusing why it comes out to that. All right, let's take a look at the other one. Again, it's the same problem as above. It's the same thing we had here, graphing. I just, cover the graph up. Let's see what happens when we try to evaluate. So when I try to evaluate g of -1, again, where is it valid? It would be valid here, because -1 is equal to, less than or equal to this. So you would just evaluate that using the absolute value. Remember, the absolute value of -1 would be +1. So this comes out to 2 times -1. So I'm sorry, I just said it comes out to +1 and wrote the wrong thing. Let me fix that. So it comes out to 1. So you get -2. And of course, you can see that on the graph. I mean, if you want to go to 1 and look down, the problem is, what if you don't have the graph? That's why I'm showing you the evaluation algebraically. So to do 0, where is 0 valid? Well, if I take 0 and try to put it in here, is 0 less than -1? Nope. Is 0 between -1 and 2? Sure is. So I'll put 0 in this portion. And remember, while evaluating a function that is only one number, the output is always that number. That's what creates the horizontal line, because you're always getting 3. So that's why you just get 3 when you plug it into that horizontal portion. So I put 2 in here because the question is, well, where is 2 valid? Because the 2 is actually here and here, but it's only valid where it equals it. So I would not use this to evaluate 2. I would use this one because it has the equal sign. So this one is also just equal to 3. So then the next question is, okay, what happens with the last part? So, some students, when they see this, they don't quite understand that I'm examining the domain, right? So I'm ignoring these. I'm ignoring this. And I'm coming over here and I'm saying, is 10 a smaller number than -1? Nope. So not doing that one. Is 10 a number that is between -1 and 2? Nope, that doesn't make sense. Is 10 a number that is bigger than 2? Yep, sure is. So now I put 10 into here. So what I've been doing here is I've been figuring out which portion of the function to select. And then once I know, I can then evaluate what to do with the numbers. So g of 10 comes out to 64. So this example, we're going to take a look at the graph and the evaluation simultaneously. And this one's a little more advanced. So if you need to stop, pause, watch again, I would advise that. So here, again, it really helps to just have a sketch of what this is going to look like on the graph. It is the cube root, so it's going to look like a sideways cube. This one is the greatest integer function, so it kind of looks like stair steps. And this one is the square root, so it'll look almost like a check mark. So now we have to figure out where the vertexes are. And these first two have very easy vertexes. This one would be at 0, 3. There is no h because there is nothing in the inside of that parentheses. And this one down here would have, remember, whatever you see is opposite for h, so this would be 2, 0. However, this one, we have to factor this b out. You have to factor b out in order to get a good idea of what h is. So when I take out that 2, it shows me that h is actually 2. So that means that my vertex is actually at -2. Okay, and so again, you might have to do this in a variety of ways. It really helps to have a good eraser. So when I do this, I'm going to go to -2, 0. Okay, and then the cube root would go 1, cube root of 1 is 1, and then 8, 1, 2, 3, 4, 5, 6, 7, 8, cube root of 8 is 2, -1, cube root of -1 is -1, cube root of -8 is -2. And you might be saying, why didn't you go by 2's on this graph? Well, remember, this 2 is going to divide the input values by 2. So where those dots will actually be located is actually within this region, because this was 1, but now it's a half. This was -1, now it's -1/2. And this one right here was 8, but now it's 4, 2. And this one was -8, but now it's -4, -2. So you might have to go back and just sort of really get a good, just write lightly and get a good idea of what that graph looks like before you start trying to erase these domain pieces. All right, so for the greatest integer function, we're going to start at 0, 3. So 0, 3 would be right here on the axis, 0, 3. And then remember, the greatest integer function just looks like a line. So it's going to look like that. For now, obviously when we come back and graph the parent function, it's going to change a little. And then when we graph the last one is going to be starting at 2, 0 with its vertex right there on the x-axis. And then the square root is 1. The square root of 1 is 1. The square root of 4 is 2. So now let's go back and start erasing parts of the domain that aren't valid. So x is less than 0. So I'm going to want to put a solid dot at 0. There isn't one. So I'm going to actually put one there. Okay, so that graph is actually going to stop there. And that's why knowing what this curve looks like is important. And I'm going to graph the graph up until that point, and then go back and erase the portions that are invalid. This one is bigger than 0, so it's gone. So then here, for the greatest integer function, I'm going to have an open circle at 0, so I'll need to change that. And then a closed circle at 2, and then I'm going to go back and draw the parent. So the parent is like a barbell looking like this. And what's interesting about that is I will have this dot sitting here because it wants a solid dot. But that's an open circle, and the graph does go to 2, and so there's just a dot hanging there. And keep in mind that this dot here, we have to go back and make it an open dot, not because of the function, but because of the domain right there. That's why it helps to label all of this before you get started drawing. So then here we have an open circle for this dot, and then it goes everything larger than 2. So that one, we didn't have to change it all. And sometimes you get lucky like that, where you get a graph that is almost ready for you before you get started. All right, and so that is that piecewise function. Like I said, a little bit more advanced. You might want to pause, rewind, watch part of it again. So now let's go to the evaluation portion. To evaluate h of 0, I need to figure out where it's valid here. And it is valid here. This is where it is true. So I'll put it into this, because 0 is less than or equal to 0. And so now I'm taking the cube root of 2 times 0 plus 4. Anything times 0 is 0, so I get the cube root of 4, which does not break down. Please don't get confused with the square root of 4. That is all it will happen with that one. So for the next one, 18, right? negative 18 is very much less than 0. So again, it's going to go here because it's true in this function. So I'm now going to take the cube root of 2 times negative 18 and then plus 4. And then I need to evaluate that using GELMDAS. So one thing at a time, inside of the grouping symbol, I will have negative 36 plus 4. That will give me the cube root of negative 32. And then I will have to evaluate that using a tree. Remember that if you have a negative cube root, the answer is negative. So I'm going to go ahead and do that part and then just make the tree for 32. So 32 is 2 and 16, which would be 2 and 8, which is 2 and 4, which is 2 and 2. Make sure you put your smallest divisible integer on the left side the whole time. You can see that I have a triple of 2's there. So this would actually be negative 2. Let's see if I can. There we go. And then root 2, so that would be 4. So breaking down negative cube root of 32, you get negative 2 cube root of 4. All right, let's take a look at what happens when we do h of 1. So for h of 1, again, we're trying to find where it is valid. And this one is going to be valid in the middle because 1 is between 0 and 2, so valid here. So I will put that into the greatest integer function. The nice thing about doing the greatest integer is if you put an integer into the greatest integer, you just get the integer back. So that will be 1 plus 3. So h of 1 is 4. So then here I gave an exaggerated number just to try to explain where would 128 go. Well, which one of these domains is 128 valid in? 128 is valid greater than 2. So I will be putting this in here. This is where it's valid. So I'm going to put 128 into the square root of x minus 2. So then I will be taking the square root of 126. And just like the cube root, I'm going to have to make a factor tree. Again, to make a factor tree, you divide by the smallest integer, put it in on the left, and then divide this. So that would be 63. By now, my smallest integer is 3. This would be 21. 63 divided by 21. And 3 and 7. What a great example of a tree here, because my pair is here, but then my roots are actually, they're not connected. They're here and here. I still would multiply them, giving me the square root of 2 times 7, or 14. Because remember, this square root and that square root need to be multiplied, giving me the 14. All right, so in this video, we're going to take a look at how to write piecewise functions from graphs. So the way you do this is you look at your graphs. If they're not color-coded, it does help to color-code them so that you can get a good picture of what you're looking at. And then what I would do is I would write out any critical points that you see. For instance, here I see a important point of a vertex at -2, 0. Okay, and then once you do that, try to figure out, well, what is that function? That function is a function f of x is equal to something squared, because it's clearly the quadratic parent function. It really helps to know your parent functions as you're doing this. And then this would be h, and this would be k. And so I don't have anything out of the parentheses, so this would simply be the function x plus, remember I'm putting a negative into an equation that has a negative, so that minus goes into a negative, makes a positive. So we end up getting, boom, there's my first function. Then you would immediately want to write down its domain. So the domain of this function using interval notation, right, it's coming from this side, so it's coming from -infinity over here, and it's stopping at -1 with an open circle. All right, so 1/3 the way done. Then look at the next one, and believe it or not, my students have the most trouble identifying a line. So that's the line, and remember, the equation of a line is y equals mx plus b from Algebra 1 or geometry. In this case, the y-intercept is 0, but the slope, let's see, the slope looks like it goes up to and over 1. So my slope would be 2. So this will be the function f of x is equal to 2x plus 0, so just 2x. It has a domain of -1 to 1 with solid brackets. So remember that if we were to use the other notation, this would have double less than or equal to signs if we use the set builder notation. Okay, so looking at the next one, looking at this one, we have a cube root. So this is f of x is equal to something cube root. Now, when I think about that, I really have to be careful about this because a lot of kids will select this as the vertex. But remember, the vertex is the point. You know how you go 1 cube root of 1, -1 cube root of -1. So this is actually my vertex right here at 2, -1. And this would be h and k. So you just want to make sure that you pick your vertex carefully when you're doing cubes or cube roots. So it'll be x minus 2. Remember, it's minus h is 2, and then -1 on the outside. This one has a domain of, starts at +1 with a parentheses, and it goes to infinity. So once I know all this, I'm just going to organize this in a bracket. So the first one, as you can see, now you might say, well, where'd the f of x go? Well, it's over here. So f of x equals these three things. The first one being x plus 2 squared. It changes the domain from interval notation to inequality notation. So x is less than, not equal to, because it's open circle, -1. Then the next one is f of x is equal to 2x. You can see that here with -1 and 1, the domain being between them. The last one being the cube root of x minus 2 minus 1, with the domain being x greater than 1. Let's take a look at one more of those. So let's take a look at this one. So here again, trying to find the vertex. My vertex is at 3, 4. Okay, and this function right here, don't go to the endpoints. The endpoints are not necessarily their vertexes. This function is the function f of x is equal to the absolute value of something, this being h, this being k. So it'll be the absolute value of x minus 3 and then plus 4. The domain of this graph is from -infinity until -2. So -infinity to -2. Again, using that inequality notation, we would just say x is less than -2. This function is a horizontal line at 2, so this will just be f of x is equal to 2. And that domain is going to be a solid bracket, -2 to 1. Keep in mind parentheses on that one. And keep in mind that this is going to be a double, it's going to be a less than sign that has an equal sign and then a less than sign that doesn't. This is the square root. I always remember the square root is kind of looking like a check mark almost. And the square root has its vertex at the end. So it kind of can get confusing. This is, in fact, the square root's vertex. And you might say to yourself, well, how do I know that's not the cube root? Well, you can tell here that it actually goes out 4 and up 2. You can see those points are labeled. So you know it's not the part of the cube root or something. So just keep that in mind and try to use all the points you have at your disposal so you don't make a little mistake. So this is h and this is k. So here we have the square root of x minus 1 plus 1. H is 1, so it's minus, k is 1, never changes. The domain of this graph is solid bracket, square bracket, 1 to infinity. So when I come down and look at the list, you can see I have that first one right there. And then I have the notation that x is less than -2, which is the same as this. The next one will be 2, between -2 and 1. Notice the solid equal sign, parenthesis, less than sign, and then the one that doesn't for the open circle. The last one will be the square root of x minus 1 plus 1, with the domain of 1 to infinity being written as x is greater than or equal to 1. All right, I hope this was instructive. I hope you like piecewise functions. They start off looking like, if you just look at this picture, you think it looks really confusing, but in many ways, they're just a good check of skills for this chapter. They're actually a very nice review problem, because if you can do this problem and everything in it, you're pretty well good for a lot of the parent function pieces that were covered in this unit.